everybody. We're going to continue today talking about our gas laws, and we're going to actually talk about one more principle before we tie all of the gas laws that we've seen into one overarching gas law. So the first principle that we're going to talk about today is called Avogadro's principle. Now, hopefully you remember back to Avogadro. We saw Avogadro's number, 6.02 times 10 to the 23rd particles in 1 mole. So today we're going to be talking, hopefully you can guess, about moles with our gas laws. So what Avogadro's principle says is that equal volumes of gases at the same pressure and the same temperature contain equal number of particles, all right? So if you have the same volume of two different gases, they contain the same number of particles. You can flip that to also say that if you have the same number of particles of two different gases, doesn't matter how big these gases are, so we could be comparing oxygen gas, which is pretty small, with krypton gas, which is a lot larger. They will take up the same amount of space. They'll have the same volume if they're at the same pressure and temperature, okay? So that's Avogadro's principle, and we actually have a formula that goes along with this. But these particles we're measuring in moles, so they contain, the equal volumes contain equal number of particles, which we're going to measure actually in moles. Now we've seen this already. At STP, remember standard temperature and pressure, and standard temperature is 0 degrees C. Standard pressure is 1 atmosphere. We've kind of briefly mentioned that, but this is kind of laying it out for you. At STP, 1 mole of any gas is equal to 22.4 liters. At STP, so 6.02 times 10 to the 23rd particles of that gas is equal to 22.4 liters. This is true of any gas or any mixture of gases, okay? So it doesn't just have to be a pure gas. Now, we've seen also this example that I've put down here, but this is just to refresh your memory and to see how this is interconnected with what we've already done. If I have the problem, what volume will 1.34 moles of a gas, any gas, at STP occupy? Doesn't matter what the gas is, right? Because equal volumes contain the same number of particles or the same number of moles. So if I have 1.34 moles, doesn't matter the gas at STP, I can convert using the molar volume of a gas at STP. Moles of the gas goes on bottom, 22.4 liters goes on top. When moles crosses out, I get 30.0 liters of a gas. Again, doesn't matter the gas. Could be oxygen, could be nitrogen, doesn't matter. All right? Now, here is Avogadro's principle all tied into one nice, neat little formula. So Avogadro's principle says that the initial volume divided by the initial N1, okay, and that's N is number of moles, so initial volume divided by initial number of moles is equal to the final volume divided by the final number of moles, okay? So pretty similar to the gas laws that we've seen. So instead of pressure or temperature, we'll just be plugging in moles, okay? Sorry, not instead of pressure, instead of temperature, we will have moles in the denominator here. All right, oops, okay. So the next law that I'm going to talk about before we go over examples is the ideal gas law. Now this is the law that nice and neatly ties all the gas laws that we've seen together into one. Now we know the combined gas law is a combination of Boyle's, Charles, and Gay-Lussac. That combined with Avogadro's principle, where we incorporate the number of moles, gives us what we call the ideal gas law. This is up here, the ideal gas law. This is the formula for the ideal gas law, and this formula works best, as you hopefully would guess, with ideal gases. Now remember, ideal gases follow the assumptions of kinetic molecular theory. But also remember, real gases don't always behave ideally. This is going to work best for ideal gases, but they don't always behave ideally. So that's just something to keep in the back of your mind, okay? Why don't they always behave ideally? Because real gases have volume. They don't have negligible volume, they have volume. And real gases do attract or repel each other, okay? But again, we're dealing with ideal gases. We're looking at how gases are going to behave, okay? So this is our formula we're going to be using to calculate either pressure, volume, number of moles, or temperature. Notice I only have 4 variables here, but you see 5 letters. That's because R is a gas constant. Now, scientists over the years have done hundreds of experiments to determine that if they know the values of PV, N, and T, if they know pressure, volume, moles, and temperature, they've been able to figure out what the R value is. Okay, now R is a gas constant. We're never going to be solving for a gas constant because we know the values of R depending on what pressure we're dealing with. So what that means is if we're dealing with a pressure that is in kilopascals, kPa, then our R value that we're going to plug in, which has been scientifically determined experimentally, that R value is always going to be 8.31, and the unit is liters times kPa over moles times K, Kelvin. Long unit, okay? If this P value that we're dealing with is atmospheres, then the R value we're going to plug in is 0.0821 liters times atmospheres over moles times K. If this P value is millimeters of mercury, our R value is 62.4 liters times millimeters of mercury over mole times K. You get the idea. Notice that the only difference, besides the values for R, but the only difference in their unit is the pressure unit, okay? That's the only difference here. Now, the reason that we have different values and different units here is because if my pressure is in kPa, I need that kPa to cancel out. So my unit here has to have kPa. If the pressure is in atmospheres, I need atmospheres to cancel out in order to solve for one of these variables. So my unit here needs to have, does us no good if this P is in atmospheres and this P is in kPa, because we can't cross out kPa and atmospheres. They're not the same unit. It's like trying to cross out or cancel out grams and milligrams, okay? Not the same unit, so you can't cancel them out, okay? So these are the R values that we're going to be seeing and working with. Let's see a couple of examples of both Avogadro's principle and the ideal gas law. So here's Avogadro's principle. It's the first problem we're doing, and I've kind of given you a slightly more complicated one than I could, only because you've already seen the gas laws, Charles Boyle and Gay-Lussac, and this is very similar, okay? So, if 65.5 grams of oxygen gas occupies a volume of 92.3 liters at a constant temperature and pressure, what volume does 89.0 grams of oxygen occupy under the same conditions? Okay, so temperature and pressure are constant. They're not changing, so they're not going to be part of our formula. What do we have here? We have 65.5 grams. This is an initial mass, not moles. Okay, so I'm going to label that M1. I have an initial volume, V1, and I have a final volume here, V2. Okay, now the issue here is that we don't have a formula that relates volume to mass. We do have a formula that relates volume to moles. So we have to do an extra step here than we might otherwise have to do. We need to convert our masses to moles. Lucky for you guys, you already know how to do this from our last unit, okay? We have 65.5 grams of oxygen. Grams of oxygen goes on bottom, moles of oxygen goes on top, and the molar mass of O2 is 32. We cross out grams of oxygen, and we're left with 2.05 moles of O2, all right? For N2, we're going to do the same thing. Our N2, or our, oops, this is not a final volume. I apologize. This is a final mass. All right, so our M2 is 89.0 grams of oxygen. I'm going to set this up exactly the same. 32 grams of oxygen on bottom, 1 mole of oxygen on top, and our grams of oxygen cancel out. Okay, and we're left with moles of oxygen. And we are left with 2.78 moles of O2. Now we have N1 and we have N2. Okay? We can calculate using Avogadro's principle the final volume. Okay? So we have V1 over N1. V1, 92.3 liters over N1, 2.05 moles, equals V2, which I don't know, I'm trying to figure that out, over N2, which I just calculated, 2.78 moles, right? Now, if you remember from our last gas laws video, we're going to cross multiply here. So, 92.3 liters times 2.78 moles equals 2.05 times V. 2.05 moles times V2. Okay, we multiply 92.3 times 2.78 and divide both sides by 2.05 moles so that that cancels out. All right, hopefully you're with me. Moles is gone. We're left with the unit liters, and we're left with V2 is equal to 125 liters. All right, now that's Avogadro's principle. Sometimes I'll give you the value, or we'll give you the values in moles already in the problem. Sometimes we give you masses, and you have to do this conversion to get to moles. All right. The second problem I have here is working with the ideal gas law. Remember, PV equals nRT. You'll get so used to saying that you'll be sick of it. PV equals nRT. Here's my problem. A steel container with a volume of 2 liters is filled with nitrogen gas to a pressure of 2.00 times 10 to the 4th kPa at 28 degrees C. How many moles of gas does a cylinder contain? Okay, let's do a little bit of labeling here. I have a volume of 2 liters. Okay, it doesn't say that any of my values are changing, so I'm not going to label these as 1 or 2. This is my volume, 2.0 liters. It's filled to a pressure of 2 times 10 to the 4th kPa, so I have pressure. At 28 degrees C, I have temperature. How many moles, this is what we're looking for, N, does a cylinder contain? All right, now just because I think it's a good practice, I'm going to put my variables list here. So P is equal to 2.00 times 10 to the 4th kPa. V is equal to 2 liters. N is what we're finding. R, we need to find our gas constant. Our pressure is in kPa. So we want to find the gas constant that uses kPa, which is right here, 8.31. Okay, so our R value here, our gas constant, is 8.31. Right? And look at our unit, liters times kPa over mole times K. Liter times kPa over mole times K. The last thing I need to label here is T. T is 28 degrees C. Now, remember, in gas laws, you need to be converting to Kelvin. So I need to add 273.1 to get, I think I've worked this out, 301 Kelvin. That's my temperature. Now I have 3 of my 4 variables and I have my gas law constant, so I can work this out. Now, here's what we're looking for, N. I'm going to say the easiest way to do this is isolate N before you plug anything in. How you do that is divide both sides by RT. RT cancels out over here, and you get N is equal to PV over RT. That's the formula I'm going to use now, okay? So over here, I'm going to go N is equal to P, 2.00 times 10 to the 4th kPa, times V, 2 liters, divided by R, 8.31. Do you need to write the whole unit? Sure you do. We need to see that the units are canceling out. So write this whole unit. Liter times kPa over mole times K. Times T. And my temperature that I already figured out is 301 K. Okay? Let's see if the units cross out. kPa, gone. Liters, gone. Kelvin, gone. The only unit I'm left with here is moles. Right? Now when you do that math, you get 160 moles of nitrogen gas. And of course, we want to make sure that we are including a decimal here because we want to show 3 sig figs. We have 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. So our answer, 160, needs to have that decimal place. That's it for ideal gases. I hope that wasn't too much. We'll have a lot of time in class to practice this. Thanks guys for watching.